design of step footings. For previous videos and this videos and PDFs, you can visit website mmsprogramcivil.com. All these videos and PDF are available on that website. It is a free website. Okay, anybody can serve the website. Today we will see design of step footings. Let's take a problem to understand that how a step footing can be designed. Design a step footing for column of size 230 mm by 525 mm, reinforced with six numbers of 20 mm dia bars and carrying an actual working load, okay, that is 1200 kilonewton. Working moment mx is 75 kilonewton meter, my is 20 kilonewton meter. So let me show you the figure. So we have a footing with a column where we have P is equal to 1200 kilonewton, mx is 75 kilonewton meter, my is 20 kilonewton meter. Okay, so the soil bearing capacity is 250 kilonewton per meter square. Use M25 grade concrete and Fe415 steel. The effective cover at the bottom steel is 75 mm. Okay, so given to us FCK is 25 Newton per mm square, Fy is 415 Newton per mm square, service load is 1200 kilonewton, assume weight of footing and backfill, that is delta P we take as 10%, that is equal to 120 kilonewton, 10% of this. Okay, safe bearing capacity of soil SBC given to us is 250 kilonewton per meter square. Eccentricity EX can be found by mx by p plus delta p, and that is equal to 56.81 mm, and eccentricity EY we can find as my divided by p by p plus delta p, which is equal to 15.15 mm. Okay, this eccentricity Ex and Ey should be less than L by 6 and B by 6. Okay, this is L by 6 and this side also you have L by 6. Our eccentricity Ex should fall in the middle third of the length. Similarly, this is B by 6. Over here there will be B by 6, and your eccentricity Ey should fall in the middle third of the width, right? Then only we can avoid the negative pressure on the footing. Okay, so let us find the area that is required for the footing. Area minimum required is service load, this is Pu plus delta P divided by your SBC, that is equal to 5.28 meter square. This formula is applicable when there is only axial load, but we know that we have two moments along with the axial load. So let us assume L equal to 2.75 meters. Okay, so once we have assumed L, that is 2.75 meters. Now this is projection A, this is projection B. This are cantilever projection in the two direction. Usually we keep A equal to B so that the cantilever action in both the direction remains the same. Okay, so A is found out to be this total L minus this depth of the column divided by 2. So this is 2.75, this is 0.525 meters. So this minus this divided by 2, this is 1.125, right? Sorry, 1.1125 mm, right? So this is how we get A. So A is found to be 1.1125 meters. Okay, now we are assuming that B is equal to A, so we can find this effective width easily. B plus width of the column, this is 1.1125 meters, this is 1.1125 meters, this is 0.23. This is how we get the width equal to 2.455 meters. Okay, so we will round this up and take breadth equal to 2.5 meters, right? So now we have L equal to 2.75 meters, B equal to 2.5 meters, A equal to 1.1125, B equal to 1.1125, A equal to 1.1125. Okay, right. Now we will check our eccentricity Ex is less than L by 6 or not. So Ex is 56.81, L by 6 is 458.33. So this is greater than this. So Ex is less than L by 6, and therefore we can say there will be no negative pressure acting on the footing. Similarly, EY is 15.15, should be less than B by 6, which is 416.66. So this is less than this. So we can say there is no negative pressure acting on the footing. So perfect. So this is okay. Otherwise, we would have to change the size of the footing, right? Now, the next step is that we have to check that whether the SBC actual is greater than or less than SBC allowable. Okay, so SBC actual can be found by this formula, that is service load P plus delta P divided by area of footing plus mx divided by zx plus my divided by zy. This all moments and loads are to be considered, are to be service loads and moments. Okay, and if of course in our case we have both mx and my, so we have to take this formula. But say if you have only one moment, that is my or mx, okay, then you have to take one this plus this. Okay, and say if you have only axial load acting on the column or acting on the footing, you can then you have to take only this much formula, right? But in our case we have both mx and my. So these are the service loads and service moments. These are the area. This is zx, this is zy. So this turns out to be 2.79 kilometer per meter square, and our SBC allowable is 250 kilometer per meter square. So SBC allowable is greater than SBC actual, so our section is safe and okay, right? Now the next step is we have to find the pressures, upper soil pressure at the four corners of the footing. So Q maximum is found by this formula, and Q minimum is found by this formula. Okay, so we are finding factored upward soil pressure, right? So in that case we have to take factor loads and factor moments, right? So this putting the values in this formula, you get Q maximum as 307.98, and similarly for factored upward soil pressure, Q minimum is found to be 215.64, and Q1 is found to be 287, and Q2 is found to be 236.58 kilonewton per meter square. Let us see in the figure. Okay, so this is our mx, this is our my, this is p, and so we get Q max over here, we get Q1 over here, we get Q2 over here, we get Q mean over here. So this is upward factored upward soil pressure acting below the footing, right? For this we have to design the footing, that is we have to give a section, or we have to design a section in such a way that it satisfies both shear and moment criteria given as per the code, right? So let's move further. So the next step is we have to assume the depth of the footing. As we know, in case of footing, the depth is governed by shear. So we will take first in consideration, that is one-way shear criteria, and from that criteria we will try to assume one effective depth, and then we will check whether that depth satisfy one-way shear criteria, punching shear criteria, and the flexure criteria, right? So let us start with one-way shear along the shorter span. So we are taking the section along the shorter span. Okay, so this is a critical section for one-way shear at a distance d from the face of the column. So this is the distance d from the face of the column. Okay, so for this section we will try to assume one effective average effective depth D. Okay, what is average effective depth D? So this is the top of the footing, this is bottom steel, this is top steel. So we will take the average effective D, which will be applicable, which will be the same for both the reinforcement, right? Okay, reinforcement in both the direction, right? Okay. So this is how, let us assume the permissible shear stress tau C is equal to 0.36 Newton per mm square. Okay, from table 19 of IS 456 2000, corresponding percentage of steel for this tau C when your concrete grade is M25 is found to be 0.25%. Okay, so this is how we get the first equation, that V allowable, that is allowable shear force, that means the shear force which is acting below the footing due to the upward soil net pressure should be less than or equal to this V allowable. So this is found by this formula, tau C into B into D. B we know that is 2.5 meters, tau C we know that is 0.36, D we do not know, so this is equal to 900 D. This is our equation 1. Okay, now averaging the stress Q. Okay, we'll see this later, just let us move forward. Okay, now to get the second equation, that is V actual. Okay, so the V actual means the shear force which is uh, acting upwards, okay, which has to be resisted by this section, which we are assuming that this V actual is equal to V allowable. Okay, so for finding this equation, this is our L1. Okay, this is D, this is L1, this is B. Okay, so we know that stress into L1 into B will give us a V, but over here we don't know Q4, we don't know Q3, we know Q2, we know Q1, we know Q1, we know Qmax. Okay, so we are just assuming and we are taking an average of Qmax and Q1 as our Q. Okay, just for the purpose of assuming a effective depth D, right? So we are average, this is what I have taken over here, assuming average Q equal to Q maximum plus Q1 divided by 2, that is equal to 297.49, okay, Newton per mm square. So taking that value, okay, over here L1, right, L1 we can find in terms of D. We know this is 1.1125 meters, so 1.1125 minus D is our L1. So this is how we get L1, right? Putting the value of L1 over here, that is Q average L1 into B, we get this equation, that is this much into D. This is our equation 2. Now equating equation 1 equal to equation 2, we get the value of D, average D, okay, that is equal to 503.66 mm, right? Now we will round off this value and we will take an average effective depth D equal to 525 mm. So this is what we are taking, this average D as 525 mm. Okay, now from that we can assume overall depth. Overall depth is equal to effective depth D plus effective cover. Effective cover given to us is 75 mm. So 525 plus 75, that is equal to 600 mm. So this is how we finalize our overall depth, that is 600 mm. Now we have to do various check and see whether this depth is satisfying all the criteria or not. Okay, now once you know your D, you assume the D, then you can find this Q4 and Q3 using this formulas. Okay, so Q4 is 273.37 and Q3 is 294.35 kilonewton per meter square. Right, now the next step is you have to find the V. So V, you can take the average, Q, you can take the average of this four, that is Q4, Q3, Qmax, Q1 divided by 4 into L1 into B will give you the shear force V, which has to be resisted by this section, right? So that shear force V is found to be 427.29 kilonewton, right? So now we will have to do the check whether our section is safe in carrying this shear force or not. Okay, so now we are finalizing this dimension. Okay, so total depth is 600. The first step depth I have given as 300 and second step depth I have given as 300 mm, right? Now this is 575, this is 538, this is 600 and this is 530. Okay, so this is what I have assumed. The section which I have assumed is shown over here. Now we have to check whether this section is found to be okay in satisfying all shear and flexure criterion, right? Fine. So I am taking a section at a distance d, right? So d is 5 to 5. So this is section which I have cut in the fitting, and this shaded area is the area which has to resist the upward shear force, right? Now, so we can find the area of this shaded portion is found to be 3187000 mm square, and nominal shear stress can be found by this formula, that is tau v is equal to v divided by area. So that is equal to 0.134 newton per mm square, which is less than tau c. Tau c assumed is 0.36 newton per mm square. So this is less than tau c. So the section is okay, right? Okay, now we have assumed the percentage of steel as 0.25. From that we can find AST required, that is 7967.5. And once we know this area, now we are assuming that we are going to provide 20 mm dia bar as our main steel. We can find the spacing required for 20 mm dia bar. The formula for finding spacing required is width of footing B into area of 20 mm dia bar and divided by AST required. This is AST required. So this is equal to 98.5 mm. Now rounding this off to 95. So we will be providing 20 mm dia bar at 95 mm center to center in both the direction. So let me show you in the detailing portion that how we are going to provide the steel in the step footing, right? So this is the initial stage. Okay, see the bottom bars are 20 mm dia about 95 mm center to center, and at this top bar in the mesh is also 20 mm dia bar about 95 mm center to center. So this is our first part. Okay, and now we have to check the one-way shear at a distance where the first step is completed, right? So now we have to take a section over here. Okay, that is at a distance of 538 mm. Okay, so let us check whether this section is found to be okay in this shear criteria or not, right? Okay, so check for one-way shear at a distance 538 mm from the face of the column. Okay, so you know the upward soil pressure diagram. From that you can find Q5 and Q6. Q5 is 272 and Q6 is 293, taking average. Okay, so I am taking a section at a distance of 538 mm from the column, right? So you can find the average of this into this distance is 0.575. This is 0.575 meters. Okay, and B we know is 2.5 meters. Okay, so from that we get V1, right? So V1 is found to be 416.875 kilonewton. Now this shear force has to be resisted by this section, this shaded section, right? So the area of that shaded section is found to be 750000 mm square. Find the nominal shear stress, that is V divided by area of the shaded section. that is equal to 0.555. Okay, so 0.555 Newton per mm square is greater than tau c. Tau c is 0.36 Newton per mm square. So this is not okay. This is not allowable. So we will have to change either the percentage of steel, or we have to increase the depth of the bottom step. Okay, so what I am doing is, okay, instead of 575, originally I had kept this as 575. Now I am increasing the length in both the direction of step 1, and I'm reducing this to 450. Okay, plus this depth of the first step was 300 mm, which I am reducing to 225 mm, and the depth for the bottom step was 300 mm, which I am increasing to 375 mm. Okay, so you can always try a better combination which gives you the best economy. I am taking in this I'm assuming I'm making this change as which I am shown in this figure. Okay, so now let me check whether my this assumption is found to be okay and satisfies the shear force and one-way shear and two-way punching shear criteria. So now let me check for this section, that is over here. Okay, so again you can find q7 and q8. You can find the average q into 0.45 into b. Okay, that will give you new v, right? That is 328. And the shaded area, now this area, okay, this shaded area, the area is, it has been increased. Originally this was 300 mm, now this is 375, right? So 375, the 0.375 meters into 2.5 meters, right? So that area turns out to be this 937500. Okay, so that is how the area of cross section has increased, because we have increased the depth. Okay, so now again calculating the nominal shear stress, that is V divided by area of the shaded cross section, that is equal to 0.35, which is less than 0.36, that is tau c is equal to 0.36. We assume tau c equal to 0.36 Newton per mm square, and this nominal shear stress is found to be 0.35 Newton per mm square, which is less than 0.36, so it's okay. Okay, so this is how we have satisfied the one-way criteria along the shorter span. Similarly, you can check for the longer span also, but it will be found to be okay, right? So it's up to you. It's better to check on both the sides. Now the next check is check for the punching shear stress. Okay, so this is our footing. This is the critical section for the punching shear stress at a distance d by 2. So the periphery length of the critical section is found to be 3.61 meters. Okay, now we have to find average q, because we have to find the shear force due to the punching shear stress which this critical section has to resist, right? So for finding that we need a q average. So for q average we can find, this is you have to take the stresses at the corner, right? Four corners. This is q minimum, this is q1, this is q max, this is q2 over here at this corner. So add all the q and divide it by 4, you will get q average, right? That is equal to 261.8 kilometer per meter square. Now we want to find the shear force. The shear force V is equal to this area minus this area, that is what I've written over here, into q average. So that is equal to 1592.33 kilonewton. So once you know the shear force which has to be resisted by this periphery section, then we know how to find the nominal shear stress. V divided by periphery into D. So that is equal to 0.84 Newton per mm square. Now, as according to code, the permissible shear stress in case of punching shear stress is given as Ks into tau c. Ks is equal to 0.5 into beta c, where beta c is the ratio of shorter span to a shorter dimension to the longer dimension of the column, which turns out to be 0.438. So this plus 0.5 is equal to 0.938. Okay, so we know ks. Now tau c is equal to 0.25 into under root fck. Fck we know is 25. This is equal to 1.25 newton per mm square. So ks into tau c is equal to 1.16, which is greater than 0.84. So the section is safe in punching shear stress. Okay, now we have to do the last check, that is for the moment. Check for the bending moment for 1 meter design strip. Okay, so for that we know that there are four different stresses at four different corners, so it becomes, the case becomes very complicated, right? So we will take the maximum stress for the design. Okay, so let me show you in the figure. Okay, so let us see the stresses. Over here we know this q max is maximum. Okay, so we'll take 1 meter strip over here. Okay, and we'll assume that below this 1 meter strip, the pressure, upper soil pressure acting is q max over here and q2 over here, right? So using this we will find the moments at different two sections. Which are these two sections? Let me show you in the drawing. We'll find first moment or at section 1, that is at the face of the column, and we'll find the second moment at section 2, that is at the face of the step, right? And we have to see in both these cases that the flexure requirement should be satisfied. So from this interpolation we can easily find q11 and q22. q11 is 290.76, q22 is 296.29 kilonewton per meter square. Now let us find the moments about section 11, which will give us a moment 11. So this you can subdivide into two parts. One is rectangular part and another is triangular part. Okay, the moment due to this rectangular part upward of the upward soil pressure, right, you will get this formula. Okay, and for this triangular portion you will get this formula. So you get finally moment at the face of the column. Okay, this is moment at the face of the column, right? You get this equal to 187.2 kilonewton meter per 1 meter width. Okay, we are taking design strip as 1 meter, right? Fine. So by using this formula, you can find D11 minimum required, that is for balance section. This we find as 232.9, but we have provided 525. Okay, the minimum D required from the flexure criteria over here is 232, but we are providing 525, means we are providing larger than required. So the section is safe in this area, right? So this is how the section is found to be okay. Once we have checked this, now the next step is we have to find the area of steel required for the moment, that is 187.2. Okay, so this is the formula for under-reinforced section. Okay, as our provided depth is greater than required, so the section is under-reinforced. Okay, so area of steel required is 1021 mm square per 1 meter width. Okay, so you can find the required spacing using this formula. We are going to use 20 mm dia bar as we have discussed earlier. So from this formula we get the spacing required is 307.5 mm, but we have already provided a 20 mm about 95 mm center to center due to satisfy the one-way shear criteria. Okay, so flexure requires 20 mm dia about 307.5 mm center to center spacing, but we have already provided 20 mm about 95 20 mm dia about 95 mm center to center, so we are safe. Okay, so nothing to worry. Now the next step is we have to check the for the flexure at section 22. So let us find the bending moment at section 22. This is our section 22, right, at the face of the step. Okay, so this is 0.45, right? So for the rectangular portion of the stress diagram, you can get this portion, and for the triangular portion of this diagram you can get this equation, right? So from this you can find moment 22, which is 30.799 per meter width, right? So again we have to check that whether the depth provided over here satisfy the flexure criteria or not. Okay, so for the balance section, the depth required is 94.45 mm, but we have provided 300 mm, so the section is okay, right? We have provided 300 mm. This is our effective depth, right? This is also effective depth. Okay, this is effective cover. So required is 94.4, but we have provided 300. We have provided much greater than required, and the section is under reinforced and also safe. So this is how we can we can see that the section which we have decided is found to be satisfying all the shear and flexure criteria, right? So the final step is that we have to draw the detailing diagram, right, which I have already shown, right? So this is how we do the design of a step footing. Okay, I hope you must have found this video useful, and let me again remind you that please visit website mmsprogramcivil.com for all the previous and this latest videos and its PDFs. Thank you.